Hello, I'm Roman, and welcome back to the series of the videos Neural Networks from Scratch in Go, where we try to dive into what the neural network is and implement all the things purely with a Golang. And in order to do this, I'm using these neural networks from scratch in Python. But again, as you can guess, I'm writing everything with a Golang. Why with the Golang, you might ask? Because why not? And yeah, in a previous chapter, in the previous video, we finished with first optimizations. The optimizations that we implemented were not that good because at first we tried to randomly find the least, set of the params that will have the best loss and the accuracy, and the number of possible combinations of the params is just infinite. Then we tried to randomly shift params a little bit, and after like 100,000 iterations, we still not that good. We can see that the loss is changing, but the accuracy is not. So I go into the next, and as the book tells us, the next thing is understanding of what the derivative is. So yeah, I think I checked this one. So let's go. The impact, and what we're going to understand today is how each neuron has its own impact on the loss. And I think that's why we need to understand derivative, then partial derivatives, and then if we take a look at we have derivative, then we have gradients, partial derivatives, then the chain rule, then we have the backpropagation, and then we have the optimizer. So I think this is what we need to know in order to being actually able to train the model, because right now we're just doing some random things and hoping that it will make the model better. Okay, let's start with the simple function, discover what is meant by impact. A very simple function is y equals to x, which takes x as an input. So there is a function. I decided not to implement this chapter in Go, because I think the goal of this chapter is just to introduce and explain what the derivative is, and I don't want to implement all of these things. So I actually launched the Jupyter Notebook. We'll see if I will need this, but at least we can play around with the code that's here and see maybe we'll reuse it. If I will need something from this chapter later through the book, of course I will get back and implement some specific function, but right now I will just, we'll try to go through the derivatives chapter and explain it as much as I can, or read it. We'll import numpy and a plotly, create an array of 5 input values from 0 to 4, calculate the function output for each of these values, and plot the results. So basically this creates a range from 0 to 4, then we create it into the numpy array. Then we actually calculate the function, and since it uses, I don't remember how it's called in the Python, but you can use multiplication of the vector for the array. So for example, if it would be a two-dimensional array, it will be applied still for all of the values in this. So, and this is the result. So you can see for the number 1, we have value 2. For the input 4, we have output 8. Pretty expected. Yes, so this is the code. Oh, and we can print X and Y. I think we do this, yes. So those are results. The slope. This looks like an output of this function. This looks like which is a line. How might you define the impact that X? How might you define the impact that X will have on Y? Some will say that Y is a double X. Another way to describe the impact of a linear function such as this comes from the algebra, the slope. Rise over run might be a phrase you recall from school. Well, I didn't study derivatives in school in English, so I don't recall this phrase. And actually, that's one of the things that I need to, adjust my thinking a little bit, because I kind of get used to the thinking in terms of the math and all of the things not in English. And for me, sometimes it takes some time just to rephrase it once again, some of the concepts in English, just, so I can put it in my head as something that is described with English words. The slope of the line is changing y, changing x, so it's basically delta y divided by delta x. It is change in y divided by the change in x, or in math is delta y divided by delta x. What's the slope of 2x then? To calculate the slope, first we have to take a 2-point line on the function's graph and subtract them to calculate the change. Well, subtracting the points means to subtract the x and y dimensions respectively. So for example, if we have, 4, then as a result, then we take in 4. Well, if we have 8 as a result, we take 4 as an input. If we have 4 as a result, we take 2 as an input, right? Division of the change in y by the change in x return the slope. So we have delta x 1, we have delta y equals to 2, so the slope we have 2. Continuing the code, we keep all values of x in a single dimensional numpy array and all results in a single dimensional array y. To perform the same operation, we'll take x from 0 and y from 0 for the first point, and 1 and 1 for the second one. Now we can calculate the slope between them. So we take in the higher differences, so we have the delta, and that's 2. It's not surprising that the slope of this line is 2. We could say the measure of the impact that is y is on 2. We can calculate the slope in the same way for any linear function, including linear functions that aren't so obvious. What about the nonlinear function like 2 multiplied by x in power of 2? Well, for me it's hard to pretend that I don't know the answer, because I know what will be the derivative here and I know why it's here like this, but I still want to recall all of these things. Approximation of the parabolic function left. So let's define another function, f2, and then s2 equals to np array from range, I would take 10 equals to from x. Then we plot to y2, right? And what you don't like. x and y must have the same first dimension, but they have shapes 10 and 5. Oh, yeah. So this is... Okay, let's... Yeah. This function creates a graph that does not form a straight line. Well, it's a quadratic function. Can we measure the slope of this curve depending on which 2 points we choose to use? We will measure various slopes. So the idea is the same. You need to get the delta y divided by delta x, and then you will have something, right? We calculate the outputs, right? So let's do the same, just to, you know, we can print 6 to print. Oh, yes, I can do it like this. I haven't used Jupyter in a while. And then we can calculate different values. So, for example, this one is 2. Yeah, but oops. Yes, and this one should be bigger. Yes. How might we measure the impact that x has on y in this nonlinear function? Calculus proposes that we measure the slope of the tangent line at x for a specific input value for this function. Given us the instantaneous slope at this point, which is the derivative. The tangent line is created by drawing a line between points that are infinitely close on the curve, but this curve has to be differentiable at derivation point. This means that it has to be continuous and smooth. We cannot calculate the slope as something that we could describe as sharp corner, since it contains an infinite number of slopes. That's true. Then because this is the curve, there is no single slope. Slope depends on where we measure it. To give an immediate example, we can approximate the derivative of a function at x by using this point and another one also taken at x, but with a very small delta L that added to it, such as this really small number. This number is a common choice as it does not introduce too large error or cause the whole expression to be numerically unstable. Delta x might round to 0 due to float point. Yeah. This lets us perform the same calculation for the slope before, but only 2 points that are very close to each other, resulting in a good approximation of the slope. So we have some delta for the x. We take in a point somewhere, for example here, yeah, and we want to calculate a slope for this point, right? Well, for the curve at this point. So then we calculate 2 values, and then we approximate the derivative, and then we take the result. As we will soon learn, the derivative of should be exactly 4, and we'll see why. The difference we see, this comes from, well, the way we calculate this, and the way the floating points are working. We chose a delta small enough to approximate the derivative as accurate as possible, but large enough to prevent a rounding error. To elaborate, an infinitely small delta value will approximate an accurate derivative. However, the delta value needs to be numerically stable, meaning our delta cannot suppress the limitations of the Python's floating point precision. It's the same for other languages, and it's based on the floating point type that you're using. For example, in Go, I think we have float 64 and float 32. So the accuracy that you can calculate for float 64 is higher, just because it's the number is way larger and you can use even smaller values and not cause some overflows and other problems with this. Our solution is therefore restricted between estimating the derivative and remaining numeric stable, thus introducing the small but visible error. So this is the error of the calculation. The numerical derivative. And I mean, that might be, it might look like, I don't know, maybe for some reason this all doesn't sound interesting, or maybe sounds boring at all, but this is an important concept to understand, and yeah, we'll see why. This method of calculating the derivative is called numerical differentiation. Calculating the slope of a tangent line uses two infinitely close points. As with the code solution, calculating the slope of a tangent line made from 2 points that were sufficiently close. You can visualize why we perform this on 2 close points with the following. Why we want to use 2 points that are sufficiently close? Large data inaccuracy. Yeah, this is the thing. For example, when we think there is, if we use this x and this x, the slope is, well, I mean, it kind of shows that it leans towards the overall direction of the function, but it's not the same. So this one is actually showing the slope of the function in this point. Continue with the numerical differentiation. Let us visualize the tangent lines and how they change depending on where we calculate them. To begin with, we'll make the graph of this function more granular using NumPy's arrange, allowing us to plot with the smaller steps. The NumPy arrange function takes in start, stop, and step parameter, allowing us to take fraction of the steps, such as, so it will return lots of the points, right? And the line is way more smooth. Let me show you the output of this one. And for example, how many items? So this is the 5,000 items in here, and this is why it's much smoother, because here to plot this I used like 1, 2, 3, 4, 5 points, and well, the plot just shows the data it connects to nearby points with a straight line. And the more The more points you have, the closer are they to each other, the more smooth the curve. It will consist anyway of the straight lines between the points. For example, instead I can use, for example, like this, right? So you can see this is way smoother. If I will use this one, it's much smoother. So for example, yes, if I have something like this, it will render it super smooth. To draw these tangent lines, we will derive the function for the tangent line at the point and plot the tangent on the graph at this point. The function for a straight line is y equals m multiplied by x plus b, where the m is the slope or the approximate derivative we have already calculated. So for example, if the, where is it? Not here. So for example, if we get the value of 4 here, it means that the line, the line that represents it will be y equals 4 multiplied by x, and it will, where is it? And it will look like this. So for the 1 we will have 4. It's better to see it on the one chart. And x is the input which leaves b or y-intercept for us to calculate. So this is actually the b is the offset on the result axis. So for example, if we have b minus 2, we have the intersection of the line with the y-axis at the minus 2. We already know x and m, but b is still unknown. Let's assume m equals 1 for the purpose of the figure and see what exactly that means. To calculate b, the formula is b equals, well, yes, and here is even the explanation. So far we have used 2 points, the point that we want to calculate the derivative at, and the close enough to it point to calculate the approximation of the derivative. Now, given the above equation for b, the approximation of the derivative, and the same close enough point, we actually calculate approximate derivative, we calculate b's, and the tangent line is a straight line, or graph the approximate derivative for f at x where x equals 2. I think you can plot it for multiple. Yeah, this is what I wanted to see. The orange line is the approximate tangent line at x equals 2 for the function. For this function, why do we care about this? We soon will find out why we care about the slope of this tangent line, but both the legend and understanding the tangent line are very important. We care about the slope of the tangent line because it informs us about the impact that x has on this function at a particular point, referred to as the instantaneous rate of change. So the higher this value, the higher the impact. We'll use this concept to determine the effect of specific weight or bias on the overall loss function given a sample. For now, with different values, so we can observe the results. impact on the function. We can continue the previous code to see the tangent line for various inputs x. Yeah, this is what I want. So we basically we generate lots of the points, we plot them, and we use different colors. We make in the straight line with the approximate derivative. So it takes the x value and the approximate derivative, well, the calculated approximate derivative, and it draws it as a straight line. And then what it does, it takes the small delta. Well, again, it calculates the derivative value, well, approximate derivative. It's called numeric version. And then we plot in some values. So basically, it calculates the derivative value for several x's. And so it's 0, 4, 8, 12, 16. And actually, even seeing the input and the output, you can guess the correlation between them. So yeah, this is for the 0, for the 1, for the 2, 3, and 4. So for example, this one had the slope or m value equals to 16. For the simple function, we didn't pay a high penalty by approximating the derivative like this, and received a value that was close enough for our needs. The problem is that the actual function employed in our neural network is not so simple. And that's true. If our neural network was like this function, that would be way easier. The loss function contains all of the layers, weights, and biases. It's an absolutely massive function operating in multiple dimensions. Calculating derivatives using numerical differentiation requires multiple forward passes for a single parameter update. Talk about parameter updates in chapter 10. So I'm not sure about the multiple, but I guess you need to do it at least 2 times with the input and with a small change, like we do for like here, but maybe because we have different inputs, we have to do this several times. We need to perform the forward pass as a reference, then update a single parameter by the delta value, and perform the forward pass through our model again to see the change of the lost value. Next, we need to calculate the derivative and revert the parameter change that we made for this calculation. We have to repeat this for every weight and bias for every sample, which will be very time consuming. Okay. So for the whole batch, like for every weight and bias and for every sample within the batch. We can also think of these methods. We can also think of this method as brute forcing the derivative calculation. To reiterate, as we quickly covered many terms, the derivative is the slope of the tangent line for a function that takes a single parameter as an input. We'll use this ability to calculate the slopes of the loss function of the weight and bias point. This brings us to the multivariate function, which is a function that takes multiple parameters and is a topic for the next chapter, the partial. Okay. So that was the numerical derivative, and I think now that we have a better idea of what the derivative is, how to calculate the numerical, also called universal derivative, and why it's not a good approach for us, we can move on to the analytical derivative, the actual solution to the derivative that we'll implement in our code. In mathematics, there are 2 general ways to solve problems: numerical and analytical methods. Numerical solution methods involve coming up with a number, find a solution like the above approach. The numerical solution is also an approximation. On the other hand, the analytical method offers the exact and much quicker in terms of calculation solution. However, identifying the analytical solution for the derivative of a given function, as we go down, will vary in complexity, whereas the numerical approach never gets more complicated. I mean, for example, like right now we just calculated for a simple quadratic function, but if it will be like a system of the functions and the functions was, for example, way higher rank, yeah, that could get way more complicated pretty fast. It's always calling the method twice with 2 inputs to calculate the approximate derivative at the point. So it's like, I would assume there is, in the numerical solution, there is no complexity growth, rather than in analytical, it really based on the function, but we'll see. Some analytical solutions are quite obvious, some can be calculated with the simple rules, and some complex functions can be broken down into simpler parts and calculated using the so-called chain rule. We can leverage already proven derivative solutions for certain functions, and others, like our loss function, can be solved with a combination. To compute the derivative of function using the analytical method, we can split them into simple elemental functions, find the derivative of those. So we can split them, which we'll explain soon, to get the full derivative. So we kind of splitting the whole function into pieces, find the derivative for this piece, and then using this chain rule to calculate the final value. To start building an intuition, let's start with a simple function and their respective derivatives. Okay, I will stop here for today and I will continue tomorrow. And tomorrow we will get through the analytical derivative and maybe we'll try to implement something. But for now, I see you tomorrow. Bye bye.